Well, thank you very much for bringing me back for the second day. It's great to be able to spread a keynote over 2 days. That way I can adjust it and improve it, and also give concluding thoughts. So yesterday I kind of talked a little bit about the landscape of parallel programming models in terms of what are the 4 basic languages that enables you to program all the different kinds of systems. Today, I'd like to conclude today with more examples of that. And you've already seen all these, you know about me and the disclaimer, so we can get past all of that. And so today I want to continue with talking about the parallel heterogeneous programming model comparisons, starting with one API. And then talk about a little bit something about OpenMP, Accelerator and Data Movement. I was involved in that, so I can give some detail about that, although the data there could be old. And then, of course, talk about SYCL data movement in terms of accessors, and of course, bring in USM. So you've seen my famous cat pictures by now. I've been told that it's never wrong to have too many cats in your pictures, but really, I actually want to talk about one API and how I break down the different parallel heterogeneous programming models out there. So with one API, that's obviously something that we gathered here today about, and it's one of the it's an important industry initiative based on standards and open specifications. It includes a unified language and library that deliver full native code performance and covers CPUs, GPUs, FPGAs, and AI accelerators. Honestly speaking, guys, this is something I've been dreaming of. And in all my talks for the last 5 years, I've always opened with something like, I wish there was one language or framework that can allow us to program all the devices kinds out there. And even in my talk yesterday, I talked about how there was a dichotomy, diversity between the languages people program with HPC and people would program for consumer devices. Well, that is now, that reality can now occur. And one API is essentially the foundational programming stack that's used to optimize middleware and framework that sits on top of it, including AI frameworks like TensorFlow. Okay. So a little bit more about one API. It includes a unified language and library that deliver full native code performance, okay? And it has frameworks that allow you to, with hopefully uncompromised native high-level language performance. And it's essentially just based on a very open industry standard and open specification, and that it would interoperate with existing HPC programming models, okay? The idea for one API closely matches what I've been looking for. It is a top-to-bottom ecosystem around one API specifications, with a specification with open source projects, with commercial products, and applications that's powered by one API. Okay, it's an alternative to single vendor solutions. One API essentially is being built to simplify development across multiple types of processors and accelerators, not just Intel. I want to strongly emphasize this is not just Intel. It can cover any other vendors that's willing to contribute. It's standards-based with an open specification to enable broad ecosystem adoption and innovation. Okay. There's a the specification includes a direct programming with an open unified language called Data Parallel C++ that's based on C++ and SYCL. It has an API-based programming with a set of performance libraries for expressing parallelism and delivering native high-level language performance for all the supported platforms. And most one API libraries are open source to encourage collaboration and help build new features and extensions. There's low-level interface to hardware, that's the one API level 0. And together, these components allow companies and Intel to build their own implementations of one API. There's this thing called oneapi.com, and that is an open call for feedback. So you might ask, why is one API being based on industry standards and an open specification important? Well, I think many people, including Intel, I certainly have this experience, had decades of experience working with standards groups in industry and academia initiatives like ISO C++, Fortran, OpenMP, MPI, Chronos, and these helps, having this group of talented individuals come together from many different companies. They help evolve the software development languages and programming models, effectively scaling forward with compute architectures. One API is a continuation of these efforts. Its open specification means that it is created and controlled in an open and fair process to achieve interoperability and interchangeability. So there is a One API feedback process that you can go to. You can look at that on the slide afterward. We do encourage this feedback. And something about data parallel C++, it's, so basically high-level languages are designed for data parallel programming productivity. And this one is based on C++ language for broad compatibility. It provides full native high-level language performance on par with standard C++. And it simplifies code migrations from proprietary languages with a programming model familiar to GPU software developers. The starting point here is SYCL, the Chronos heterogeneous programming framework, being developed under the industry consortium. And Intel is addressing gaps in the language through extensions that they're going to drive into the standard and include source code to source code compatibility tools to assist with migration, for example, of CUDA code to DPC++ code. So it currently leverages well-known LLVM compiler technology. Alex Bader is now working to improve, adding this capability in LLVM, as well as Intel's historical users leaderships in compiler technologies. And there's going to still be a need to tune for each architecture still. So it is based on C++, and it will have Intel's extension as well as ISO C++ extensions going into it. So a little bit about the One API specification libraries. For the API-based programming, performance libraries can span several workload domains that benefit from acceleration. So library functions are custom coded for each architecture. So no developer tuning is required when developers migrate code between supported architectures. For API-based programming, there are libraries that's already included, including, of course, the math kernel library for matrix algebra, FFTs and other math operations, thread building block and DPC++ library for parallel algorithms and data structures, analytics libraries for classic machine learning and statistical functions. There are deep neural network and machine learning combination libraries for optimizing deep learning frameworks like TensorFlow, and video processing library for optimizing video codecs and processing functions, as well as render libraries for visualization. All right, so finally, a little bit about API, one API level 0. It's a primary low-level, close to the metal driver interface for language runtimes and libraries with fine-grained control over accelerator capabilities. It's aiming to be low latency and high-performance interface to device with a multi-threaded design, and it's open source and it's standardized. So there are a lot of people involved in this. There are more than 30, maybe even, at least when I looked, more than 30 companies now supporting the One API concept. And many of these companies are participating in Intel's beta release and providing feedback on its tools. So let's continue on. I wanted to talk about what are the different kinds of parallel programming models there are, so you can discriminate between them all. So question is, how do you represent the different forms of parallelism? It turns out that in my experience, I can roughly break them up into directive-based or explicit parallelism-based, task and data parallelism, queues versus stream-based. And under the directive versus explicit, I've had experience in almost all of these, being the CEO of OpenMP at one point, and I was deeply involved with the interaction with OpenACC, and that is mostly a directive-based programming model. So here's an OpenMP example where you have to use something like POM Pragma OMP parallel for, and it's essentially a compiler transformation of the code to be parallel based on the pragmas. The other one is using an explicit API, and that's primarily what most of the other ones do. SYCL, CUDA, TBB, Fibers, C++ 11 threads, all use some sort of API. And here I'm using a C++ AMP example of using an explicit API like parallel for each. Okay, each one of these language, as I've shown for C++, has this capability. And so you might wonder, subtly, what's the difference? Honestly speaking, we now know that for the most part, having explicit API is give you better coverage of intention and a separation of concern. Whereas if you look on the left side, you see that single parallel for, it basically in that one statement encapsulates all the intention, all the concerns, including where, when, how you're doing the parallelism. And while this is a great way to get you started incrementally, and that's exactly what OpenMP was designed for, it doesn't allow you to separate concerns easily. I know because I actually wrote some of the compiler work for that when I was with IBM. And honestly, it was really hard generating error messages because you really had trouble figuring out where that pragma is attached to based on the entity following it. Now, there's also task-based versus database parallelism. And honestly, this is not so much as saying one language has one and the other one doesn't. Most language have some forms of both. And so OpenMP and Threads, TBB have capability, for example, to support task-based, where you can do multiple tasks performed in parallel. Okay, and then finally, there's also database parallelism, which is what I've shown on the right with C++ AMP, CUDA, SYCL, C++17 parallel STL, where the same task is performed across a large data set. Now, that's not to say that OpenMP doesn't have data parallelism, or that CUDA or C++ doesn't have a task parallelism. They do, but they have slightly, so most languages now understand that there is requirement for both to some degree, okay? And then also there's a separation between whether command groups or kernels are queued or streamed along. So most, in terms on the left side, like C++ AMP, CUDA, and SYCL C++17, parallel SCL, have functions that are placed in a queue and then executed once per enqueuer. So here in this case, you have essentially, using CUDA as an example, CUDA malloc and a vector add, and the vector add kernel is the function that's going to be placed onto a queue. There are also, on the right, languages where a function is executed on a continuous loop on a stream of data, and examples of that is Boink and Brook GPU, okay? So let's move on to one of the biggest limiting factor in parallel and heterogeneous computing, and that's data movement. The cost of data movement in terms of time and power consumption. So it can take considerable time to move data to a device, and this varies according to architecture. The bandwidth of a device can impose bottlenecks, and this reduces the amount of throughput you have on the device. And the performance gain from computation, if it's greater than the cost of moving data, then usually you won't do it. So if the gain is less than the cost of moving data, it's just not worth moving that data. And most languages have some ways of saying, if it's greater than this many or less than this many iterations, don't bother doing it. There's an OpenMP pragma that does it, and most of the language have some ways of controlling that. Many devices have a hierarchy of memory regions, like global, read-only, private data. Each region might have different size, affinity, and access latency. And this is where the optimization and acceleration experience of various people and the talks that you have in here will tell you that information. So having the data as close to the computation as possible absolutely reduces the cost. So how do you move data from host CPU to a device and back? So I actually gave a talk back in 2015 at LLVM about the OpenMP 4.0 device construct. And in the middle, you see that this is actually one page that tells you all the OpenMP accelerator constructs, believe it or not. It's not that many. And most of the constructs is dealing with data movement. The top bullet is dealing with, I know you can't see it, but don't worry too much about it. The top, you can find the talk easily. The top bullet is talking about the command to move the kernel to the device. The middle bullet, all of those four commands are dealing with data movement, explicit data movement. And then the bottom bullet is dealing with specifics that has to do with distribution to NVIDIA devices. And really, almost 60% of the command is dealing with data movement in this case. And so the question, and you can look at that later on, I won't go through it. I hope it doesn't start. Okay, good. Okay, so with implicit versus explicit data movement, the data is essentially, with implicit, the data is moved to the device implicitly via cross-host CPU device data structures. And usually the runtime mediated so that data is moved just in time to the compute device as necessary. With explicit data movement, data is moved to the device. You have to explicitly call an API to do it. Okay, so SYCL and C++ AMP is an example of how data is moved to the device implicitly. Okay, and OpenCL, CUDA, and OpenMP is an example of how data is moved to the device explicitly. Now, having said that, I want to give a caveat that many of these programming languages have now crossed to the other side because they all recognize that there's a requirement for both implicit and explicit data movement. For example, as I'll show with USM later on, SYCL has now brought in the ability to do explicit data movement. And both OpenMP and CUDA have brought in the ability to do implicit data movement using unified address space, for instance. So let's go to the next slide. What's going on? Okay, I thought I crashed for a moment there. Okay, so this is an example of the code in C++ AMP that does it. And then on the right, you can see the explicit CUDA memcopy host to device and CUDA memcopy device to host command that is explicit. Okay. So OpenMP accelerator and data movement, the second part, I want to show quickly what an OpenMP accelerator and how data is moved. This is just a piece of warning. This is on OpenMP 4, which is the latest OpenMP, I think is 5 or 6, I can't remember. It's going to have new additions and changes. I left OpenMP when it was 4.5. So basically, the OpenMP accelerator model assumes that a computation node has a host device connected with one or multiple accelerators as target devices. And it uses a host-centric model in which a host device offloads code regions and data to accelerators for execution, specified using the target construct. So this construct causes data and an executable to be copied, offloaded to the accelerator before computation. Okay. Now, I want to also contrast that with another well-known system that I called out as one of the more commonly used languages that's suitable to program your many different configurations. That's Chronos OpenCL. Here, essentially, you have one host and one or more OpenCL devices, and each OpenCL device is composed of one or more compute units, and each compute unit is divided into one or more processing elements. So the memory is divided into host memory and device memory. Now, if you map that onto OpenMP, it will look like this. In OpenMP language, the target on the far right allows you to send construct to onto the device. There's also a parallel for SIMD on the left, where you can run on processing elements plus the vector units. And then there are two specific ones that's aimed at NVIDIA-like devices, where there's a hierarchy. And teams essentially construct to create a league of teams with one team of threads on each compute unit. And then there's a distribute clause to assign work groups to teams. Okay, I'm going to show quickly how that looks like. But one of the big thing, as I called out, is the data movement. The data environment is lexically scoped, and the data environment is destroyed at the closing curly brace. So allocated buffers and data are automatically released. So conceptually, what happens is from the host, you have to call OMP pragma OMP target map to allocate memory, 2 to move to the device, and 4 is essentially to move from the device. There's also another one called update, which allows you to update the host in the middle of computation in the device. Okay. So going back to our SAXPY for CPU in OpenMP, it's actually quite simple. If it's for the CPU, you just have to add pound pragma OMP parallel 4 on top of the serial SAXPY. I know I pronounced it SAXPY, sorry about that, calculation, and you get the job done. Given an input of the number of elements in the vector, the scaling factor, the first input vector, and the output and the second input vector. Now, building up the serial system is quite simple. Obviously, there's the explicit data movement across the top. Okay. Now, if you want to do target, if you want to do it on the accelerator, you're going to have to add some sort of data environment. And then you would have to create a mapping to the device. And because I'm doing this, on a coprocessor and accelerator, then I have to call teams, which essentially creates a single thread in a team of threads that essentially acts as the trigger for creating a distribution of those threads. Okay. I'm not going to go too much into distribution, but in the distribute, you can now distribute into a number of blocks. And then in the parallel for, it creates a work share with Barrier now this time, where all the members of the teams are active to work on that particular serial, that particular kernel. Okay. Now, the last two is necessary if you're an Intel device. This is all that you need. Sorry, the last two is necessary if you're an NVIDIA device. This is all that's necessary if you're on an Intel device. Okay. And I won't explain the intricacies of that, but that was the state of it when it was in OpenMP 4. They might have updated that. But this is how you would distribute across using Pragma with data movement. Okay. So let's go look at what SYCL does. With SYCL Accelerator, and this is the third part, and data movement, and I'm going to talk deeply about accessors and USM. So SYCL basically aims to make data locality and movement efficient using the implicit data memory movement. And what SYCL does is it separates the data storage and data access. So there is the separation of concerns. So SYCL has separate structures for accessing data in different address spaces, and it allows you to create data dependency graphs from that. Okay, so when you separate data access, you can create a buffer which have accessors for a CPU, another accessor for GPU, and the buffer basically allows type-safe access across host and device. And the accessors are used to detect dependencies. And so let's say you're copying or allocating memory in some address space. So there's a global accessor for memory stored in global address, in global memory. There might be a constant accessor for memory stored in read-only memory. There might be a local accessor for memory stored in group memory. And then now you have to build a data dependency task graph, which is familiar to many people, especially in high performance computing, these DAGs. And what happens is if you have multiple kernels, A, B, and C, you might have buffer A, which accesses a read accessor in kernel A. And then kernel A outputs its result through a write accessor to buffer B. Kernel A, buffer A also has a read accessor in kernel B and write to buffer C. And then you would put the results together so that kernel C has a read accessor for B and C, the outputs from kernel A and B, and then generates the results through a write accessor to buffer D. And this would look something like this. The runtime would interpret this graph as something that looks like the bubbles on the right. So the benefit of these data dependency graphs is that it gives you the ability to describe your problems in terms of relationships rather than single statements that would need to be enqueued explicitly copying things around. You won't need to do that. Synchronizations can also be performed using a closure style of RAII, where you automatically copy data back to the host only if necessary. So this was one of the big things in a lot of the other languages, trying to decide when to not do the zero copy, meaning so that you don't do unnecessary data movement. Okay, so you have to, it also removes the need for things like the complex event handlings and like dependencies between kernels are automatically constructed. And it allows the runtime to make data movement optimizations. The runtime can see the graph, so you can preemptively copy data to a device before kernels. You don't have to, you won't move data back to the host unnecessarily just because the user told you to do that. So this is what so just to go through quickly what SYCL would look like with this. This is a very simple example. Many of you guys have probably seen it, but there's a reason why I want to go through this. It's just your similar SAXPY, but in this case, it's just a vector add. And what I'm doing is, of course, I'm setting up the include for SYCL HPP, and then I would set up the buffers, okay, and create the buffers to maintain the data across host and device. And then the buffers synchronize upon destruction. I would set up a queue to enqueue the work. I would create a command group to define an asynchronous task. And then the scope of the command group is defined by a lambda expression from C++. But before I do that, I would set up the accessors for the dependencies. In this case, I have two reads. I have a read for the input and A and input B, and I have a write for the output. Okay, so these accessors give access to the data on the device. And then I would call a parallel for passing in a kernel with a lambda expression for the range, for the range. So here I'm essentially creating a parallel for to define a kernel, and then I would do the computation. This is exactly what the serial computation would look like. Okay, and in this case, I would access the data via the accessor's subscript operator. And it looks very natural, very much like what you would think. And though in some cases you have to provide a name for the lambda, okay, this is because lambda expressions in C++ is not a standard layout type. So when you're passing things between host and device, they may not be laid out the way you think. So with a name, you can now track back and figure out which is the real kernel that came from your host. Now, having said that, though, I'm happy to announce that SYCL 2020 has now made that capability optional for certain compilers. Other compilers might still keep it. For instance, I know that DPC++ doesn't require it now. So the actual kernel is quite simple. I'm sorry, the actual calling program is quite simple. It's just a main with the input, initializing the vectors, and then you would call parallel add, which is exactly what this one was. So having said that, so what happens here is that the result is stored in output upon returning from the parallel add. So having said that, I have to say that's really nice, except in some cases, I still want to have pointers. So here's a slide which I love to call to say how I learned to stop worrying and love pointers. Pointers are a fact of life in many existing C and C++ code. Interesting program operate with more than just arrays apart. And rewriting C and C++ program to augment with buffers and accessor is a bit of a pain for new programmers and large programs. And along with this, if we have an in-order queue, you can enable things like porting to from CUDA or any explicit data movement type C++ framework, especially the one that is very much using pointer-based programming style. And when you have, and this is the case when you have a simple program or you simply don't care about data dependencies, or when you're building some other framework on top of SYCL that requires explicit control data movement. We've had some experience with building other frameworks like HPX and Cocos, things like that, or other people have experience with that, building them on top of SYCL. And they just thought that in those cases, those frameworks actually want explicitly control over the data movement. So in this case, we want to actually take the same data, the same information, and deconstruct the SYCL vector add. You see that in red, these are all the stuff I had to add for SYCL, even if I was just using a pointer. I have to build a buffer around the pointer, a C++ object. I have to build this accessor dependency graph. And the access have to be declared and used instead of pointers. And all of our pointers became buffers, essentially. So this leads me into what is USM. So this is Unified Shared Memory. This name is actually derived from OpenMP 5.0, I believe, where they have unified address space. And this is the idea of supporting pointers in SYCL. Effectively, it requires several capabilities. One that is single unified virtual address space, supporting pointer-based data structures, pointer-based memory management, and explicit data movement and shared memory allocations. So this is what the first point is about. In order to support unified virtual address space, so USM memory allocations essentially returns pointers which are consistent between the host application and the kernel functions on the device. Okay. And representing the data between the host and the device doesn't require creating the accessors, and essentially is a pointer-based API that's more familiar for C or beginning C++ programmers. Okay, so in this case, you can see that in the host memory allocation, it's accessible by many devices and the host, and that it does not migrate between host and device. There are shared allocations possible, and that's accessible by at least one device and the host, and that might migrate between host and device. I'll show what that means. So here's a pointer-based structure. The data is moved between the host and device in a span of memory in bytes rather than a buffer of a specific type. The pointers within that region of memory can freely point to any other address in that memory. So this is a lot easier to port existing C or C++ code to use SYCL. And the memory, and with the explicit memory management, it means that the memory is allocated and data is moved using explicit routines like memcopy. So moving data between the host and the device doesn't require accessors or submitting the command groups. And the SYCL runtime will not perform any data dependency analysis dependencies. And the dependencies between commands are going to be managed manually. You can also have shared memory allocations. So some platforms will support variants of USM where the memory allocations they share the same memory region between the host and devices. And there's no explicit routines are needed to move the data between the host and the device. Okay. So USM allocation types, USM essentially has 3 different kinds of memory allocations. A host allocation is allocated in host memory. A device allocation is allocated in device memory. And a shared allocation is allocated in shared memory and can migrate back and forth. So USM basically has 4 variants, which a platform can support with varying levels of support. Each SYCL platform and its device will support different variants of USM and different kinds of memory locations. So at the minimum, you have to support explicit USM, which has consistent pointers, a pointer-based structure, and explicit data movement. But you can optionally move towards restricted USM, which has shared memory allocation, which I talked about here, okay? And then you can also, so that even though they're shared, they cannot be accessed concurrently between the host and the device. But you can also go to the next step, which is concurrent USM, where they can be concurrently accessed. And then finally, to system USM, where the system allocations can be accessed. So having said that, I want to point out that what I just said about USM is a SYCL 2020 feature. We're so confident of it, we're unveiling it early. And with that, I wanted to talk about this roadmap of SYCL, where in 2020, we plan to release first a provisional that's already done, and it's in public review right now, and you can take a look at it, and you can take the feedback, give us feedback, which will lead to a final in Q4. We plan this version to be based on C++ 17. This means that it enables existing C++ features such as class template argument deduction, popularly called CTAD, and deduction guides that makes code far less verbose. There are also a number of other great features, which I'm going to highlight. You're going to see that we released SYCL 1.1 in 2017, and previously 1.2 in 2015. And if you were astute, you're going to predict that we seem to be settling down to a cadence of releasing new releases every 1.5 to 3 years, and you would be right. That's matching to ISO C++ schedule. This is because we have adapted to a bus train model delivery, just like ISO C++. You're going to see that we have changed the naming scheme from aligning with OpenCL version to naming by year to allow us to be based on multiple backend options in addition to OpenCL, which remains our primary backend. You're going to see that we're projecting, tentatively of course, that a future SYCL will be released after 2021, the exact version to be named later. And will likely be based on C++ 20, which will be released at the end of this year. This shows essentially our tighter ISO C++ alignment, injecting our heterogeneous knowledge into ISO, along with many other frameworks, I'll admit as well too, and adapting C++ features. So I want to show what a pleasure it's been to see SYCL grow since 2016. By my count, starting from when I first attended in Frankfurt to the last meeting in Barcelona before we shut down, we have doubled in size by 2 times, from averaging 15 people to over 30 people on the list. I'm really proud to be to be part of this group of insanely talented people from many different companies. We continue to have strong attendance from Intel, Xilinx, Codeplay, AMD, ARM, Qualcomm, A&L, University of Salerno, and University of Bristol. And while we were in Barcelona, we were invited into BSC actually to visit their facility. So thank you, BSC. Externally, we have been active in CPPCon, giving SYCL talks and tutorials. We just gave one in CPPCon 2020. But we've been giving it since 2016. We have also had BOFs in SC 17, 18, 19. This year, we were lucky to be accepted for one of the 13 precious BOF. So you're going to see, I just gave my recording for that, talking about SYCL and ISO C++. There used to be 88 BOFs when it was physical, but because it's virtual, they're only allowing 13, and we were lucky to be one of the few. In the last year, we actually had a separate standalone BOF, and for SYCL and one for ISO C++. So this year we combined them both. Okay. At SC19, the number of SYCL events exploded from 2 to 3 SYCL events in 2018 to 6 to 8 that I counted in 2019, in terms of papers, talks, keynotes, BOFs, and various workshops, including the Intel One API introduction workshop that happened just before SC19. So as you know, in the past, SYCL held an annual workshop called DHPC C++. I know it's a mouthful. We don't claim to invent nice acronyms like RAII. So that was in IWACO, as it was not yet its own working group. So I'm going to claim the September 22nd, 2019 as SYCL Independence Day. That's when it became its own working group, and now it's held as an integrated conference with IWACO called SYCLCon. And Rod Burns is dealing with a lot of that, leading through bringing all of that to reality. So this is the main slide. It shows what might be in SYCL 2020. I keep saying might because even though I'm pretty sure, but you know, legally speaking, I have to keep using the word might. And in the top right box, you see our general larger philosophy that we have followed in our change from SYCL 121 and SYCL 2020. We want easier integration with C++17, less verbal language that has smaller code size and simplify common patterns. We want to enable multiple backends, but simplify interoperability, while at the same time ease porting of C++ applications to SYCL, improving programmability. We want to aim to strike a balance for performance and stability by enabling backwards compatibility with previous release. So we expect any API breakage to be minor from 121 to 2020. On the top left, you're going to see some of the features that we already have. And there's going to be talks in this conference about that. I draw your attention to generalization, program modules, host tasks, unified shared memory, in-order queues, as well as NVIDIA backend implementations for CUDA and PTX. In the bottom right, you're going to see there are many features in the pipeline. And on the far right, you're going to see our main goal is converging SYCL and ISO while continuing to strongly support OpenCL, driving to support many more kinds of chips, similar to the one API goal. The main diagram illustrates our philosophy of moving from SYCL 121 to SYCL 2020 and iterating the cycle with new releases every 1.5 to 3 years from previous to the next release. So this highlights the already large and growing SYCL ecosystem, starting with the implementations on the left. Then there are, which covers the Tricycle, One API, Data Parallel C++, Compute CPP, HIPSYCL. Okay. Then there are the many research papers. And of this, I want to point out the Exascale computing project and Celerity for SYCL cluster. And now I see that there are many more that I'm going to have to add for next year. The Celerity programming environment seeks to enable developers to scale C++ application to Accelerator clusters with relative ease, while leveraging and extending the SYCL domain-specific embedded language. By having users provide minimum information about how data is accessed within compute kernels, Celerity automatically distribute work and data. It's kind of like MPI for SYCL, but it's done in C++, and I love this project. So next one is ECP, I want to call out, is accessed within the compute kernel. ECP basically allows SYCL to run on exascale supercomputer systems using Intel chips being built at Argonne National Lab using DPC++ and one API. And it's aimed at reaching exaflop computing. That is 10 to the 18 floating point operations per second. There are now also several benchmarks involving SYCL. I want to call out University of Bristol's Babel stream that measures the performance portability of SYCL, along with other popular acceleration languages such as OpenMP, OpenCL, CUDA, and OpenACC. Over time, this has increased to a suite of 4 to 5 benchmarks, including TLEAV, that measures acceleration performance. There's also Intel Jeff Hammond's Parallel Research Kernel, PRK. It's a suite that contains a number of kernel operations that basically measures productivity, how easy it is to port to various languages. Most of the code here relies on open standard programming models, which including SYCL, and can be executed on many computing systems. There are also many libraries for linear algebra, machine learning, and parallel acceleration frameworks. And at the bottom, you're going to see the active working group companies that are attending the calls regularly. So in this slide, I want to point out what an extraordinary adoption it's been to see SYCL grow into the HPC space, something that I've always wished it would happen. And it did with the help of this wonderful, enormously talented working group. And that happened with the Aurora supercomputer in exascale computing, part of the Coral 1 project. Okay, I attribute this to the fact that we lead ISO C++ with a language that uses standard C++, but augmented with heterogeneous dispatch, something that ISO standard C++ won't have until for another 6 to 10 years, I suspect. So, but they do have elements of it, as I've shown in my previous talk. So this is the promising road to get to exascale computing using accelerators, computers using Intel processors. Now, there are actually 2 more coming in Coral 2 at Oak Ridge and Livermore. They're called Frontier and Al Capitan, and they will be delivered with AMD processors. Now, we don't know what the programming model yet is for those, but I will point out that SYCL can run on ROCm, as one of our implementation is HIP-SYCL, and that's demonstrated to work on these processors. So SYCL implementations are many, okay? There's compute CPP, there is tricycle, there's HIP-SYCL, but on the far left, something that came within the last 2 years is DPC++, Intel's One API, okay? And they all fit within the CPP Clang LLVM, mostly Clang LLVM framework. Just like C++ is the language, SYCL is the language. And C++ has implementation in GCC, EDG, Clang, and Visual C++, and one that I used to work on, IBM's Excel compiler, okay? But so these are also implementations of SYCL language. And finally, one more thing. I wanted to, so one more thing. This is the last slide, last couple of slides. Okay. So I talked about which programming model works on all the architectures, and is there a pattern? And I talked about the fact that really it's OpenCL, C++, SYCL, and OpenMP. And that I want to summarize that SYCL is entirely standard C++, OpenCL is C99, OpenMP is C, Fortran, and C++. SYCL and OpenCL compiles to Spear, but SYCL 2020 can also compile to other backends like Vulkan, OpenMP, PTX CUDA, or other proprietary ISA. And they're both multi-compilation models. Now, looking ahead, SYCL separates the storage and access of data and has both implicit and explicit data movement. OpenCL, OpenMP, C++ also has explicit data movement. SYCL, OpenMP, C++ are single source. OpenCL is separate source for host and device. SYCL, in its implicit data movement, creates automatic data dependency graph. C++ parallelism is still fairly low level, from which all the parallelism can be built right now. OpenCL is higher level. And SYCL is the highest level, but this means some parallel patterns are not yet available, and higher level means greater productivity. And lastly, SYCL, OpenCL are an explicit parallelism model. OpenMP is a directive-based programming model. SYCL and OpenCL are the most ideal of any kind of platforms in an open environment and follow C++ and C closely. C++ allows this separation concerns and is ideal for general purpose programming. OpenMP is most ideal for Fortran and older C code bases and doesn't allow separation of concerns. DPC++ is an implementation of SYCL within one API. It's something I've always dreamed of, to program all device kinds on one language. I'm going to skip this, but I want to bring up this last slide, which talks about the upcoming relevant DPC++ and SYCL talks that immediately following on Wednesday at 11:30 is the SYCL performance and portability. And then on Thursday, there's the tutorial on One API and DPC++, which is an essential series hands-on. And then later on in the afternoon, there's going to be more tutorial on the DPC++ new features, including what I just talked about, like USM. And then on Friday, the 16th, there's going to be a full afternoon tutorial session on developing SYCL using DPC++, including how to run this code on NVIDIA hardware. And then, of course, on Monday, bring your own code along to this Intel workshop and works to bring it to One API and DPC++. So I hope that everyone comes to this, comes to these, as well as all the other great talks that's been happening. And I'm certainly watching them and learning a lot from them. So with that, I'd like to say thank you to everyone. And thank you for having me. And if there's time for any more questions, I will certainly stay in the Slack channel or answer them here. Thank you very much. Cheers.
Thank you very much, Michael. That was a really great talk. And we have 1 or 2 minutes left, 2 minutes or 3 minutes left for questions.
Okay. Are there any questions? I know that this is kind of a fire hose.
So in the Zoom chat, there is no question, as at least I can't see him. And in the Slack channel, there's no question yet. So please use either the Slack channel, or if you have an immediate question, you may raise your hands and we can give you the mic.
I can ask one question, and it's all about MPI. So how MPI is going into this all scenario? Is it like, will it be same or it will be completely different?
Okay, so there's in the HPC community, thank you for that. The question is, how does MPI fit within this whole scenario? So obviously MPI works on a distributed systems, usually across networks or interconnects. So there always have been talked about MPI plus X or maybe OpenMP plus X. So soon I suspect there will need to be talk about DPC plus plus or one API or SYCL plus X. And how does that X handles in terms of a distributed system? And we've been working with the possibility of other systems that does the distributed part of network much better. And these are things like, there's things like TaskFlow from Utah, as well as HPX from Hartmut Kaiser, which is distributed all in a very C++ specific framework. And that's why that we have been collaborating with them to bring the reality of possibly load balancing across discrete network GPU, CPU devices. You see, SYCL actually allows you to load balance within the same device of the CPU and the GPU resource. But so I am quite interested in seeing how MPI, and of course I mentioned Celerity, and Celerity essentially is doing something like that. So I would point you to that research direction in terms of going towards a full distributed heterogeneous one API.
So as you know, MPI is basically the C++, there is only just wrappers. So I'm not sure how C++ advanced features could be helpful in that. They will be using underlying the C, basically.
Well, that's exactly the problem. We don't think MPI works exactly right as it stands, because it is primarily a wrapper on top of a communicators and ranks. So that's why I think that's a slightly different approach is useful, and that the ones that I mentioned are totally different approach that is not using anything like that. Okay, so have a look at things like HPX, have a look at TaskFlow, have a look at Celerity, and see how they're doing it.
Sure. Thank you.
Yeah, you're welcome. Good question. All right, well, thanks. Please stay tuned and continue to watch the channels and the rest of the talks. Take care, everyone.